When the observable universe reaches its most visible peak, scientists believe that we may be able to see as many as 2 trillion galaxies. That's 2 with 12 zeros. And what's more, this number doesn't even consider the fact that most of these galaxies have hundreds of billions of stars, the vast majority of which have solar systems like ours. This all occurs over an expanse of 93 billion light years, the diameter of the observable universe. However, some estimates suggest that the totality of the entire unobservable universe could exceed over 20 trillion light years in diameter, over 200 times bigger and millions of times more voluminous than what we can observe. Imagine how many galaxies could fit within that expanse. With these crazy numbers in mind, it's very likely that, somewhere in creation, a planet with near identical environmental features to our own could exist. We know this now more than ever given the sheer number of Earth-like planets within a few thousand light years of us, let alone within the entire expanse of the universe. As such, humanity has been looking to find these Earth-like planets for several decades now, as we aim to find the first planet worthy of acting as a second natural human colony. Sadly, we will never have the time, or reach, or capability to find the most Earth-like planets in the unimaginably vast universe. But searching for Earth-like planets, much more locally, has been a central focus in both our never-ending quest to find intelligent life beyond the Earth, and also to make potential contingency plans for the distant future, when we may be forced to leave our current homeworld. In the 20 years since we discovered the first planetary system beyond our own, we have learned that most of the estimated 400 billion stars within the Milky Way galaxy have solar systems with at least one planet. On top of this, billions of these stars are G2 type stars that are similar to the Sun, which accommodate rocky planets that share similarities with the Earth. With rapid, unsustainable climate change and overconsumption ripping through the natural resources of the Earth, the requirement to get off this planet and spread around the stars is increasing, and so locating the most Earth-like planets orbiting Sun-like stars within a distance of a few dozen light years would be a sensible first step. Notwithstanding the impending doom of our own civilization, Earth-like planets are so intriguing to scientists because those orbiting within the habitation zones of these stars may support water on the surface and stand a much better chance of accommodating resilient, pervasive and evolving life, and perhaps intelligent life. So surveying the most Earth-like planets out to a distance of several thousand light years may help us refine our search as we look for natural and engineered signs of intelligent life. A planet or moon that shares a similar size, composition and temperature to the Earth, and that could hold the conditions for sustaining life as we know it, is known as an Earth analogue, minus the UE part if you live in the United States. Such candidates for consideration are measured via the Earth Similarity Index, which takes mass, radius and temperature into account when considering our cosmic clones. Though we have been searching for Earth analogues around the galaxy for some 2 decades now, the consideration and awareness of Earth analogues dates all the way back to the 1850s. Around this time, Mars and Venus were both hypothesized by astronomers to have similar conditions to the Earth, and thus may host their own planetary civilizations alongside our own. Of course, the launch of the first space probes in the 1960s dismissed any possibility of Martian or Venusian civilizations, but even then, we continued to act as if Earth analogues existed. The search for extraterrestrial intelligence, now a globally established and ongoing effort to scan the skies for alien signals, unofficially began with the advent of radio in the early 1900s, and we have been listening out for distant signals that could be emitting from Earth analogues supporting life ever since. It wasn't that long after that we actually picked up the first evidence of a planet in 1917, but our lack of understanding at the time caused us to dismiss the findings as an already documented astronomical event. Towards the end of the century, in 1988, the first suspected detection of another planet was noted, when variations in radial velocity were detected around the star Gamma Cephei AB. These fluctuations were indicative of what we now understand to be an exoplanet with an orbital period of about 2.5 years. However, inaccurate overestimations of the star's size caused astronomers at the time to adopt the belief that these fluctuations were the result of the star's rotation, and it wasn't until 2002 that follow-ups of the case's evidence was finally understood to show a planet orbiting the star. 4 years after the initial detection, we did actually manage to find the first conclusive proof of an extrasolar planetary system, when in 1992 a system of planets was observed to be orbiting a rapidly rotating millisecond pulsar some 2,500 light years away, named PSR B1257 + 12. With this knowledge, a rapidly improving technology and investment in space observation and exploration on a global scale, we now know that there are as many as 100 billion planets in the Milky Way galaxy, and that billions of these have potential habitable conditions to be Earth analogues capable of supporting life. But estimations only go so far. We may know of planets that could support life, but there's a lot of guesswork involved, and even then it doesn't really achieve either of our aims of finding another race or finding a new home. To identify the most viable candidates for both, and to achieve more definitive answers, would require a more intensive and clearer survey of the stars. The initiative to find Earth-like planets has been boosted by the rapid progress we've made, and the attention that has been given to it. This was evident in March 2009, when NASA launched their world-famous Kepler space telescope. A space telescope is exactly what you'd expect. The same mechanics largely, but with a few added features and the ability to gain unfiltered, unrestricted omnidirectional views into the stars and beyond. The Kepler spacecraft was also armed with advanced hardware and algorithms to automate a lot of the processes humans once performed, which were subject to error. The objective? Survey our region of the Milky Way galaxy and find the most Earth-like Earth-analog exoplanets orbiting within the habitable zones of their respected stars. In the past, we haven't just been able to aim our telescope at a star and see vibrant planets akin to artists' conceptions that you see in news articles and on the internet. No, sadly, there's a lot more mathematical estimating involved. Astronomers instead measure the luminosity of a star and wait to observe a dimming. A very mild dimming or light fluctuation is usually indicative of a comparatively small object, most likely a planet, passing in front of it and blocking out a small portion of the light, and scientists then reverse engineer these fluctuations to determine the size and chemical compositions of the object. The advantage of the Kepler spacecraft is that it can automate a lot of this process. It can perform billions of processes within a short space of time, and so can analyse much finer detail in depth that humans would otherwise miss. This meant that the Kepler Space Telescope would have the capacity to pick up hundreds, if not thousands, more Earth analogues than ever before. The original mission was commissioned to take 3.5 years, but it was extended by a further 6 months in 2012 when the level of noise interference caused measurements and observations to be completed at a slightly slower pace. However, by mid-year that same year, one of the 4 reaction wheels malfunctioned and the spacecraft lost its ability to be able to turn. Despite the massive restriction this placed on the mission, it was continued for a further 10 months before a second wheel failed, which disabled the collection of scientific data. A few months later, in August 2013, NASA announced that they had given up trying to remotely repair the 2 wheels and the mission was abandoned, but the craft remained floating through space, destined to roam about the solar system. Even though the mission had been called off sooner than expected, NASA were delighted with the results, but the exploration didn't stop there. Despite the craft being rendered useless for all intents and purposes, it remained able to detect objects around red dwarf stars, among a few other narrow-scope features. 1 year on from cancelling the official mission, NASA accepted a proposal named K2 to restart the mission on a smaller scale. This strategy was implemented, and so the Kepler spacecraft began collecting data again. Though it was a fraction of the unit it once was, that didn't stop the spacecraft from creating one of the biggest astronomical mysteries of recent times, when in 2015 it detected drastic light fluctuations from a star named KIC 846. With the light dimming by as much as 22%, planets in orbit couldn't explain this whatsoever, and the cause was ruled to be a large object experiencing regular change. It was this hypothesis that sent the astronomy world crazy when people started to speculate over the possibility that the Kepler spacecraft had picked up the first evidence of an alien megastructure being built some 1,600 light years away, most likely some form of Dyson structure. This curious case still retains global fame today, but several natural hypotheses have eased the immediate urge to investigate the case further, and until proven otherwise, solar dust is believed to be the primary candidate. In total, the Kepler spacecraft observed 530,506 stars and catalogued 2,662 extrasolar planets over 9 years of functionality, before the fuel supply to the reaction control system ran out and the craft was deemed officially retired on the 30th of October 2018. With the combined efforts over 20 years, we have now identified over 4,000 planets believed to be of similar sizes and compositions to the Earth, orbiting within the optimal zones of their host star. A small sample of these, including many that the Kepler telescope observed, were taken to form a list of the most Earth-like analogues that could hold all the right conditions for sustaining life, and could give us a clearer picture of just how common or rare life, and indeed intelligent life, as we know it is around the Milky Way. Though we don't know the makeups of these planets for certain, given they are too far away to actually observe in any great detail, it's likely that at least a handful of these are of very similar sizes, shapes and makeups to the Earth. This means that water could exist on the surface and atmospheres could be oxygen rich, which it could be a sign of organic photosynthetic plant life. We've made very little progress in determining the probability of intelligent life, but that isn't to say that some of the most viable candidates aren't fascinating discoveries in their own rights. Of the 500 plus Earth analogue candidates flagged by the Kepler team, 12 have diameters between 1 or 2 times that of the Earth and orbit within the habitable zones of their stars. 9 of these 12 candidates orbit G-type stars that are of very similar sizes and surface temperatures to the Sun. On a broad scale, given the diversity and irregularity of what's out there, these planets are impeccably similar to the Earth. Perhaps the most identical to Earth is Kepler 438b. Located around 640 light-years away and orbiting a red dwarf, this planet is the champion of the Earth Similarity Index, taking the #1 spot for the most Earth-like planet discovered to date. Size is an important component of the ESI, as a very large rocky planet will have a strong gravitational field, and such intense gravity makes it less likely that life like us could exist on the surface there. Gravity has a fairly negative impact when increased. Astronauts on the International Space Station have to exercise for 2 hours a day in order to build and maintain muscle, as the gravity of Earth can start to damage and wear away their bones if they acclimatise to the weightlessness of space. As such, scientists look at planetary radius as a key indicator of what type of hypothetical life could exist there. Though not as optimal for supporting human life, another candidate is the recently discovered GJ273b, also known as Luton b. This Earth analogue has excited scientists due to its proximity to the Earth. At 12.2 light-years distant, Luton b is right around the corner from us. It is, as of the making of this video, the third nearest believed habitable planet to Earth. Knowing this, about 18 months ago, SETI's sister not-for-profit organisation, METI, beamed a powerful radio signal in its direction. The signal contained musical compositions and information about science here on Earth, lasting a couple of minutes. Though some of the information could be lost as the signal grows fainter over its interstellar journey, any intelligent alien life that detects it should theoretically be able to acknowledge it as an engineered broadcast and identify the exoplanet in the general direction from which it came, providing their technology is of a reasonably comparative level to our own. If this unlikely chain of events occurs smoothly, a flash of radio energy, akin to the infamous WOW signal of 1977, could pass over the planet in reply sometime in the early 2040s, would most likely be our first direct interaction with intelligent alien life. Rocky planets with water on the surface that could support life may rely on patches of dry land to give intelligent life a chance to thrive, but not every Earth analogue has continents and land on the surface. Kepler 22b is a planet roughly twice as large and massive as the Earth, orbiting the 638 light-years distant star Kepler 22, a G-type star almost identical in composition and size to the Sun, at about 85% of the distance Earth orbits from our host star. Kepler 22 and the Sun share some incredible coincidences. The star is estimated to be only 3% less massive than the Sun and only 2% smaller in physical size. Its surface temperature is also estimated to be merely a few hundred degrees hotter than our own star and is probably about 600 million years younger. Though we haven't been able to observe Kepler 22b in enough detail to make a clear judgment, there are a few possible surface compositions that could exist. Should the planet lack any sort of atmosphere, its surface temperature could be minus 18 degrees Celsius. However, if an atmosphere is present and causes the same greenhouse effect we face here on Earth, then the surface temperature could be around 22 degrees Celsius, notwithstanding the possibility of large fluctuations across the planet. Given the observations we have made, if Kepler 22b is indeed an Earth analogue, then not only does it allow for liquid water on the surface, but its surface would be entirely covered in liquid water. Yes, Kepler 22b is believed to be an oceanic planet, with little to no rocky formations on the surface. Either that, or its temperatures are close to Venus levels. Both are possible theories, but until we can look a bit closer, we'll never know. But if it truly is an ocean-only planet, then imagine the possibilities for diverse marine life that could exist beneath its waves. Just think of how varied and spectacular marine life is on this planet, and we've only managed to fully explore 5% of our oceans. Imagine what could be waiting for us on the depths of this planet, let alone an ocean-only world twice as large. Certain theories put forward contest the idea of how deep the theoretical oceans on Kepler 22b would go, but most agree that the pressure at certain depths would be so immense with the sheer volume of water that beyond a certain event horizon-like point, water would be so densely compressed that it would turn to ice. However, this would not be traditional ice, but instead would be a specific type that is not dependent on temperature, known as Ice 7. Ice 7 is a crystalline form of ice that can be turned into a solid at room temperature with 3 GPAs of pressure acting upon it. 3 GPa meaning a pressure of 30,000 times greater than that of Earth's atmosphere. While other Kepler Earth analogues could potentially house intelligent life as we know it, planets like Kepler 22b may house just as many mysteries for fascinating possibilities for primitive marine life. Let's just pray that they don't have their own version of the Megalodon. There are a whole host of other Earth-like planets out there, and these 9 other candidates stick out and are being studied and investigated further. But there is still one more candidate, one incredibly Earth-like planet. Even though it doesn't top the Earth Similarity Index, it certainly has scientists buzzing. Kepler 452b is an exoplanet about 1,400 light-years from Earth, located around a star in the constellation of Cygnus. Fairly remote given some of the other Earth analogues, but that has done nothing to waver scientists' interests in the planet. It has been given multiple complementing nicknames, the most common being Earth 2.0 and also Earth's older cousin. It is estimated to be about 60% larger in diameter than our homeworld, orbiting at 105% of the distance of one astronomical unit, with an orbital period of only 5% longer than our calendar year, meaning 1 year on that planet is approximately 385 days. Its host star, Kepler 452, is about 1.5 billion years older than our Sun, while being slightly larger and about 20% brighter. Given that the star, and hence its solar system and so potentially its exoplanets, are so much older than the Earth, astronomers are hopeful that the estimated 6 billion year lifespan could give a much more realistic chance to life for emerging. It took 4 billion years of life rising and falling before humans emerged, and so any prospecting system we find may be unlikely to support intelligent life the younger it is. But in a system that's much older, the chances of habitability turning to habitation are increased. Discounting the stages of planetary formation and the cycles of habitability on rocky planets, 6 billion years orbiting within a star's habitable zone would allow for a very good chance of life as we know it. While not conclusively proven, there is a high chance that Kepler 452b is a rocky planet, and while its mass has not yet been determined, its size could be indicative that the planet's gravity field is a lot stronger than the Earth's. This could present a challenge to any humans in the distant future who wish to colonise it, as stronger gravity fields are incredibly taxing on organic skeletal structures due to the same restrictions faced by those astronauts manning the International Space Station. The same phenomenon spells trouble for humans landing on Kepler 452b, as the effect of bones wearing down and mobility being lost may be increased by living on the surface of a larger rocky planet. A good indication of how we would cope may be evident in the near future, when the first people living on a future Mars colony would return to Earth after several years or even decades. Keeping this in mind, any life there might actually be quite a lot larger than us, having adapted to survive and thrive under a harsher gravity field. Imagine the size of the dinosaur race that could be living there. This isn't a problem we'll have to worry about for a while, however. Even on the New Horizons spacecraft, it would take over 25 million years to reach their star systems. There are a fair few advancements in technology that would need to happen before science turns its attention to interstellar space puberty. With planetary targets identified, the mission is now clear. Find a suitable planet and colonise it. The sooner the better. We've identified plenty of Earth analogues, but there are still millions more out there to discover. During that search, and until a spacecraft like the Kepler craft is launched again, we will continue listening from Earth. Radio observatories rely on the Earth's rotation to pick up faint signals from relatively short distances, and Earth analogue or not, there is always that faint possibility that we may stumble across a transmission from another race. The Very Large Array is a set of radio telescopes working together as one big interferometer. Each satellite dish is about 80 feet wide, and there are 27 separate dishes, giving it a survey area of about 13 square kilometers of the sky at any given moment, and this area moves as the Earth rotates. Of course, listening for signals isn't the only technology that stands to be refined in the coming decades. Our capabilities of physical telescopes will increase, giving us a clearer picture of the stars as opposed to just radio images. The Overwhelmingly Large Telescope, or OWL, was an enormous telescope proposed by the European Southern Observatory with a staggering 100-metre lens. This project would have been extremely expensive to proceed with, however, as it would require a very complicated construction over an extended period of time. As such, the project now lives on as the European Extremely Large Telescope, at a still very impressive but much smaller 39-metre lens, under construction now and due to become fully operational in 2025. Scientists and participating governments alike hope that this telescope will allow for not only the observations of light fluctuations to detect planets right here on Earth, but that the telescope will be large enough that we may be able to start imaging particularly large extrasolar planets. But observing and cataloguing is only a very small part of the process. At some point, either by opportunity or by necessity, we will be forced to leave Earth and find a new suitable planet to support the billions of humans expected to live within the next half a millennium. We've identified a multitude of suitable candidates, but the problem is the distance they are from Earth. Even Luton B, one of the nearest planets, would take over a decade to reach at the fastest speed in the universe possible. With modern methods of propulsion, the scale of the problem is amplified exponentially. Even Proxima Centauri, the nearest neighbouring star to the Sun, which we know has no real potential for supporting life in its planetary system, would take a staggering 19,000 years to reach, let alone the distances of 200 to 2,000 light years. The metric is nearly impossible. A less improbable option would be to limit our selection of planets within the solar system to candidates such as Mars or Venus, although this rules out the possibility of habiting an Earth analogue by nature. Both Mars and Venus present difficult obstacles to overcome. Both lack a breathable atmosphere, and both are exposed to lethal doses of radiation from the Sun's unfiltered rays. Both have very poor surface conditions for organic life, not to mention the fact that Venus has a very poisonous atmosphere. In practice, we could sustain a small human colony of up to 1 million people on Mars with modern methods of technology. In fact, this is exactly what has been planned for under the hypothesized Mars colony proposed by Elon Musk's SpaceX. Over the next few decades, we could take a very gradual stream of people to begin to build a robust colony to help accommodate a research mission on the surface of the red planet. But what if we need to sustain millions or billions of humans there? Well, in that case, we would definitely need Earth-like conditions which do not exist on the surface of Mars. But nature isn't always a definitive law. As we have done many times here on Earth, it could be manipulated, altered and adapted to our advantage. Of course, for all intents and purposes here on Earth, we generally only alter nature on a very small scale. Altering the nature of a planet that has been barren for hundreds of millions of years would require a more large-scale form of planetary engineering, known as terraforming. The hypothetical process of terraforming has become a relatively well-considered topic among astrobiologists, with the possibility of colonising Mars. This process involves turning a fairly barren or uninhabitable planet into a life-supporting Earth analogue by flooding it with chemicals so to globally alter its climate and create a breathable atmosphere that is safe for humans. Of course, this is an enormous ask of engineering. Even Mars would require an almost impossible amount of resources in order to make it truly Earth-like, not to mention the technical barriers we still have yet to overcome. But it's not an impossibility for the future. It is thought that, in its early life, Mars once had similar surface conditions to the Earth. The red planet also orbits at the edge of the habitable zone of the Sun, meaning that water was once most likely on its surface. Even now, glaciers have been observed on the surface, which could weigh in its favour as a suitable candidate for our next home. There have been a few proposed methods as to how we might begin the strenuous, resource-consuming process of terraforming, although none are yet achievable by modern methods of technology. They all involve deliberately inducing climate change through certain chemical compositions that would enhance the greenhouse effect and contain warmth within an atmosphere. One powerful greenhouse gas that could be used is ammonia. While we would need untold quantities of the gas, it could be obtained within the solar system. Many planets on the outer rim are believed to hold frozen deposits of ammonia. If we found a way to collect it all and then blast it into Mars's atmosphere, we'd begin the process. However, current estimates show that any induced atmosphere would break down after a few hours and leak into space. An alternative gas we could use would be methane, large quantities of which exist within Saturn's moon of Titan, among other places which are somewhat more local to Earth. But like ammonia, an atmosphere driven by methane would only be able to exist for a very brief period of time. Alternatively, we could begin launching missiles at the planet. CFC gases are highly detrimental here on Earth, but hypothetically we could use a barrage of missiles containing the gases to warm Mars's surface. On the other hand, this would require 170,000 tons of CFC gases annually, consistently barraging for little over a decade, and this would totally destroy Mars's ozone layer. Other ideas include spreading dust on the surface to reduce albedo and flooding the planet with extremophile microbes such as algae, which have been observed to survive under Martian-like conditions for periods in excess of 1 month. But the same problem always emerges. Eventually, all the heat and chemicals are lost into space by leaking out through Mars' atmosphere, and we know of no way to stop this from happening. These problems are blockades in the short term, but technology moves quickly. Just think of the advancements we've made in 200 years. Perhaps, even within our lifetimes, we may see more viable methods of terraforming arise. When viewing the Earth from space, it becomes easy to see just how insignificant we truly are. One planet, one moon, one chance. We float through space as part of only one planetary system, and with the amount of risk that carries within a galaxy, it's easy to see why so many scientists are keen to find alternative methods and destinations in our quest to leave the Earth. Our search for the sky for other planets is still a bit immature, and improvements in technology will surely allow for better analysis of our nearby cosmic neighbours. The challenge thereafter would be reaching an Earth analogue, or engineering an otherwise unsuitable planet to become one. At the moment, terraforming seems like the innovation we might crack first, but presently, neither are possible by current scientific methods. It's quite impactful to look up at the sky and see so many planets the human race could thrive on, but with no way to get there. A good practice to adopt in the meantime would be to focus our efforts on looking after our own planet. With unsustainable climate change ravaging the world faster than the technology to leave it is improving, some proponents of the doomsday curve believe our civilization needs a major shift in attitude, either towards technology or away from wastefulness. The day may be on the horizon when humanity is technically sophisticated enough to blast towards another celestial body and set up colonies there, but the truth is we have no idea what could be waiting for us upon arrival. We have no idea whether Earth analogues could host foreign diseases too strong for humans to survive on their surface. We don't know if terraforming is even possible on a planet as far gone and barren as Mars. We have no idea if near light speed travel, an essential breakthrough in getting around the galaxy, is even possible. As illustrious as our search for Earth analogues has already been, we don't know if those planets will ever be reachable, and we might well be hedging our bets on a fleeting illusion. In the meantime, we must act as better stewards for our own planet, as no Earth analogue will ever be as perfect for humanity as the Earth itself.